is being given by Dr. Joyee Ghosh. She is a faculty member in Department of Physics, IIT Delhi, and she is working in quantum key distribution, fiber, as well as free space. She has developed entangled photon source at communication wavelengths, and she has many projects, just not one project. She has three, four projects, and she is PI of all the three projects. She is working on silicon photonics, like quantum photonics using silicon, and then she's working on this waveguide-based entangled photon source in communication wavelength, and along with that, rotation frame invariant free space QKD. So these are the major projects. She might be having more. She's quite active, having a very vibrant group. And before joining IIT Delhi, she has been Marie Curie Fellow in ICFO, Barcelona, Spain, then Humboldt Fellow in Germany, University of Saarland, and postdoc at NST, Maryland. So he has vast experience in quantum science and technology. So today, Joyee is going to talk about entangled photons, quantum optics experiment, and quantum information applications. So, Joyee, it's to you.
Thank you, RP. Thanks for that kind introduction. And thanks to Professor Panigrahi and the entire team of QIQT for giving me this opportunity to speak in this forum. I also spoke last year. It's really a pleasure to participate in this summer school and, talk about, a broader aspect of the field that we work on. There are many experimentalists as well as theoreticians who are working currently in this field, and it's a pleasure to share this forum and speak about our endeavors in this. So I'll start. Is my slide visible? Just a quick. Is it visible?
Joyee, it's visible. Yeah, you are audible. Slides are visible. It's full presentation mode. Yeah, don't worry. Go ahead.
So I'll just move this part. Yeah. Somewhere here. Yeah. Okay, so actually, maybe I just want to minimize this 1 second.
You're looking for pointer.
Pointer, yes, now I'm looking for pointer, but there's some tab that's coming on the top.
Participant is enabled. You can close
anyway,
this, I think.
By the way, do you see the cursor?
Your cursor I can't see here on the screen.
No.
I can't. Now I can see. You move the cursor. Let's see whether it's moving your cursor.
I'm moving the cursor.
No, cursor is not moving on your slide, but it's there at the top left corner, but it's not moving.
Trying to find the laser pointer then. Maybe I'll just start. It's getting late. So actually I'm going to talk about, as RP already mentioned, so today it's a little broader. So we'll talk about several things. So I thought the befitting title is Entangled Photons. So quantum optics experiments, and there are several QI applications. I work on a few of them using a couple of techniques. So we'll be deliberating on that. So the outline of my talk is this. Since this is a summer school, I thought there are many students who are present here. That's why I wanted to start with a small introduction, a little bit of quantum optics, then just touching upon quantum information. This is maybe it's not required for the audience as much, but this just flows in the context. And then entanglement and single photons as quantum systems, entangled and single photons as quantum systems. Then the techniques of producing single and entangled photons, the popular ones, the workhorse techniques that we use in the lab routinely to produce these photons. And then I'll be talking about recent studies from our group, mainly about the quantum communication experiments involving these entangled photons, the highlights from our quantum photonics lab in IIT Delhi, And today, actually, I mean, I try to give a quick update. So this is a part, as RP already mentioned. So we also work on silicon and insulator nano waveguides, and pretty much in collaboration with our faculty collaborator, Professor Vivek Venkatraman in electrical engineering. So it's actually a group, our group, we share it with him as well. And so I'll be also talking because we have good results there as well. So all of that. And if there's time, then we'll also talk about a small, like it's one of the fascinating experiments in my experience. And it's pertaining to quantum networks. So if there's time, we'll also talk about just a couple of slides there. So let me start. This is, actually, as part of quantum information, so quantum optics is actually like we can visualize it as the mother, because this field in quantum information, there is of course the and the computational part of it, but there was a lot of so quantum optics was actually very broad, and because of developments in quantum optics and new things that people started exploring in the optical regime of quantum, after those things became evident, the field of quantum information actually flourished all the more, because there was prospect of using photons for several of these applications, and also to realize certain fundamental experiments, because photons were easy to use in comparison to other kinds of qubits like atoms or spins and all of that. So that really popularized the field of quantum optics. So what is quantum optics? So it's just not classical optics, but something more and different. It's the science of non-classical light, as we say it, and any science that combines light and quantum mechanics. So this is the field, and it is a subject that deals with optical phenomena that can be only explained by treating light as a stream of photons rather than as electromagnetic waves. So that is the set notion, waves, light. But today, as we know it, if we picture, like if there are also regimes, and then there is the wave particle duality. So there are also regimes where light behaves like a particle, and all those things are very interesting. So the subject of quantum optics is actually as old as quantum theory itself, but in practice, it's a relatively new one. It has come to prominence in the last quarter of the 20th century. It's a highly specialized subject, but the demand for the subject is very broad, as I mentioned. The interest in the subject is strongly fueled by the prospect of using quantum optics in quantum information applications and quantum technologies, in particular quantum communication, quantum computation, all of that. Right, so that's why quantum optics is hot, and people need to dig a little deeper into the subject for understanding it. So this is a very overall, very very general description of the subject, and we will not have time to dig into very deeply of coherent states and Fock states and all that. So let me just begin. What is light? A wave or a stream of particles? That's the question. So we take the question seriously. So we test each hypothesis through experimentation.
Sorry,
So as
we
we
see
know,
only first slide.
sorry.
So we don't. We see only first slide. So the
Yeah,
entangled.
do you see only the first slide?
Yes.
Oh,
It's
now do
not
you?
moving, yeah. It's not moving, yeah, right. I thought you were just giving introduction, that's why I didn't say anything.
No, 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 no. I'm moving.
Yeah, it's not moving. I think that's why this
Let me
pointer
reshare.
is
No?
also
Let me
frozen.
reshare it. I'll just reshare. I'm so sorry.
Yeah.
Yeah. Good that you. I don't know why it's not moving. Uh,
Yes.
Does it show now?
Yes,
Yeah,
we see.
it's showing now. Yeah. This is slide number what? It's
No,
moving now.
I'll go back a little bit. So I started with this one. Do you see the outline now?
Yeah, it's
Yes.
okay. You can go ahead.
So
These
I
things
go
should
ahead.
cover.
I actually
Yeah.
went through all these slides, but these are just very
Yeah.
introductory. And so I'm here. Uh,
Yeah.
the wave behavior, right? So interference and the double slit experiment, these are signatures of the wave behavior of light. I'm trying to make it full screen. I hope it's, is it still visible? This current slide?
It's visible.
And
Current
the
slide.
next one, RP, I
Ah,
changed the slide. Do you see the
no, it
next?
has not changed. It has not changed. It's stuck
So
here.
if I go to full screen, somehow this is a problem. So I'll go back.
Don't
Maybe
go to full screen.
yeah, I
Yeah.
don't go to full screen. Do you see the next slide now?
Yeah, it's visible now. Next slide. Yeah.
And I changed it again. Yeah.
Yes,
Okay.
we see the
Yeah.
cursor also.
Yeah.
Okay. I'm sorry for this problem, but yeah, so we don't go full screen. So yeah, so interference, diffraction, these are key signatures of wave behavior. The key signature of particle behavior as we know it is like, you know, the photoelectric effect, although for its explanation, quantization is not required, but it was like the first particle, you know, the particle behavior of light became evident from the photoelectric effect and also with the Compton effect. So in these in particularly in the particle aspect, one thing that is highlighted is that light can be absorbed or emitted as quanta, which we know as photons. So there is this property of indivisibility, because now if you imagine a single photon and there is a beam splitter here, right? So the photon can either go through or it can get reflected, right? So it cannot be divided into both parts, right? Because it's a single, you know, it's like a particle aspect, and there comes the particle behavior. And utilizing that particular property, actually, there are several other experiments or results, as we know, like also the anti-bunching experiment and all of that. So key signature of a single particle behavior, basically. So it can show both particle aspect as well as wave aspect, right? So let us see this simple you know, experiment. This is a Maxender interferometer. So so there is a single photon input, let's say, and you have a beam splitter, and then there is a mirror on the reflected arm as well as on the transmitted arm, as we know, and then there is another second beam splitter that combines the two beams, and in the end of on the two output ports of the beam splitter you have single photon detectors, let's say. Now if you run the experiment and you do it as a function of this phi, which is the phase shifter, we would see, and if you collect it over a long time, so let's say you collect it over typically, let's say, half an hour or something like that, right? So you see, I mean, although there are counts that are revealed, there is an interference pattern that crops up like this. So this is on the y-axis, you have probability of detection, and on the x-axis, you have the, as a function of this phase phi, you will see that there is a pattern, which is, you know, a sinusoidal pattern. So it's like an interference pattern. So that tells you that even if you start with a single photon input, you see a pattern like this. So this is like it's like a wave behavior, and this pattern will only show up if you accumulate over a long time, right? So that is one important part. Now the same experiment, let's say if we remove the second beam splitter such that you don't allow the beams to superpose, right? You don't have a superposing device, and you just collect it through single photon detectors PD1 and PD2, then there is just, you know, irrespective of the phase of this phase shifter, we see that there is a 50% probability for single photon detector 1 to click, as well as there is a 50% probability for detector 2 to click. And there is no pattern that comes up. And this shows a particle behavior. So it's really what you do with the experiment that you can really dictate if you want to see the wave behavior or you want to see the particle behavior. And these are actually interesting experiments that we do in the lab. And it's really bizarre that, you know, it can behave in either way. So this is actually the wave particle duality. And there was a very interesting question that came up, and it bothered physicists actually in the past. And the question was, does the photon know when it hits the first beam splitter, if we are doing a wave or a particle experiment, and then behaves accordingly? Does the photon have that intelligence already before we do the experiment? So in order to answer that question, so there was this Wigner's Gedanken experiment, or the delayed choice experiment, which was an experiment to decide at random whether to put the second beam splitter only after the photon has passed the first beam splitter. Now, this is a thought experiment. It's a Gedanken experiment, as you can imagine. But if we could do this, probably we could decipher. Right. So anyway, so those are interesting reads from the past, because people used to bother, what is this ambiguity? So, that's like the duality. So now there are three regimes of description as we know it. There is the classical picture. So when we are talking about light, there is a classical picture, fully classical picture, where we take light, atoms, everything classically. Then there is a semi-classical picture where light actually interacts with material or atomic system. Light is considered to be classical, but the material system is quantized. So typically you talk in terms of atoms, discrete energy levels, and so on. And then there is a fully quantum picture where both light as well as matter, they are quantized. Right. And this is in this third picture, actually, we require quantized light. And therefore, this is actually the picture that is mostly used in the field of quantum optics. Now, some of the optical phenomena in nature that we know that can be only explained by quantizing light, that means taking the fully quantum picture, are some of these effects. These are spontaneous emission, lamp shift, Casimir effect, spontaneous parametric down conversion, photon anti-punching, and there are many others in the list. Just to give you a glimpse of all of this, so spontaneous emission, I think everybody knows, there's not much to deal with it, but this is one of the simplest phenomena in nature, as we know. So every atom, so atoms have, stationary states. And this is, let's say, imagine an excited state. This is a ground state of the atom. If you give it some energy, and energy that is resonant, it's going to get excited and go to this level. Now, once this is there in that level, since these are stationary states, the atom is supposed to reside there and not get de-excited. That's the definition of stationary states. But however, we know that, although classically it cannot be explained, quantum mechanics, like if you quantize light, we know that there is the presence of vacuum fluctuation everywhere. So every system is actually interacting with the vacuum, and this fluctuation actually stimulates your system and stimulates this particular de-excitation process, due to which it happens in nature. So after a certain time, which is defined by the natural decay time of the atom, this atom gets de-excited to the ground state, and we know that there is an emitted photon, which is called as the spontaneously emitted photon or the fluorescence photon, and this is a natural thing. And there is a broadening, which is called as natural broadening. The width of that emitted radiation actually gives you the lifetime of this energy state. And this is also dictated by the energy time uncertainty in quantum mechanics, as we know. So every energy level is actually not a delta function, it's not a discrete level, but there is some fuzziness around it, and that's the delta E, which is the energy uncertainty. And related to that, this level is not infinitely long-lived. This has a certain temporary lifetime, and that's given by the spontaneous emission lifetime, as we know. Now, there's another effect, that is lamp shift, that requires the explanation through quantization of light. And this was an effect that was discovered by Willis lamp. And it says, the effect tells you that there is a difference in the energy between the two energy levels, which is 2s half and 2p half in the hydrogen atom. And this was not predicted by the Dirac equation, according to which these two states should have the same energy. But because Dirac did not take into account vacuum energy fluctuations, and if you take that into account, actually there is a small energy shift between these two. And so that gives rise to what is known as the lamp shift. So this lamp shift plays a very significant role through vacuum energy fluctuations, as we know, through also in the theoretical prediction of Hawking radiation from black holes, right? Apart from other things that are important. Now, another important effect is the Casimir effect. So this is a very interesting one again. So it is an effect that, if two mirrors are placed very close to each other in vacuum, then they are automatically attracted to each other. And this is the Casimir effect. And it is named after the Dutch physicist Hendrik Casimir. And in quantum field theory, actually, this is due to a physical force that acts on these macroscopic boundaries, as you can see from this picture, in this confined space, which arises from the quantum fluctuations of the field. So this macroscopic physical force, this physical force due to the Casimir effect arises from the vacuum fluctuations which are present everywhere. So now another effect which is very close to people who are working in quantum optics, and particularly with, for the generation of single and entangled photons, is spontaneous parametric down conversion. This is a nonlinear optical technique. I'll be detailing this later. So I'll just to give you a gist. So this is one technique that, according to which, it requires vacuum fluctuations that actually stimulates your system and allows a pump photon to split into two daughter photons, which are called signal and idler. And these two photons are correlated by birth, as we know, through frequency, through energy. There is conservation of energy and momentum, and this can be utilized for since they are correlated, so you can have them entangled. You can also have single heralded single photon source based on this, all of that. So, but this effect cannot be explained again classically as we know it. If you start from the Maxwell's equations, this effect cannot be explained. And so this SPDC is an effect that takes into account, again, the presence of vacuum fluctuations. And another thing we know is photon anti-bunching. So this is again, it has to be quantized light and anti-bunching. Again, this is an experiment that utilizes the beam splitter. So if you have a single photon, again, if it's a truly single photon and you have a beam splitter and there are two detectors, detector 1 and detector 2, and then you want to see the coincident counts between these two detectors, that means counts that are at the same time. So the detectors 1 and 2 click at the same time, and therefore you have a coincident event. So these events are plotted. So this is a typical graph that shows this event, and it is a function of the time. So at time t equal to 0, they should be, since if it's a, let's say if it is two photons that are impinging a beam splitter and these two photons are born at the same time, then you could have an event. But if it's a single photon source, which is truly single photon, then of course you will never get any correlation event, because either detector 1 would click or detector 2 would click, because a single photon again is indivisible. It cannot go two parts, and therefore this is the famous anti-bunching result. And this is an anti-bunching curve that people usually do it routinely as characterization of their sources in the lab, whether it's a heralded single photon source or a true single photon source based on a true, natural source, like such as a single atom, or a quantum dot, which is an artificial source, or other kinds of sources of true single photons. So again, it's a signature of the quantized light. Maybe a brief history of quantum mechanics. There has been several, starting from the black body radiation of Planck, and then there are several effects. There are actually milestone experiments in this. This little detail, but I thought I would just highlight this. So the quantum optics actually bagged several Nobel Prizes. Some of these notable ones, the ones were without all these aspects wouldn't have been possible. So in 1997, it was Stephen Chu, Claude Cohen-Tenuji, and W.D. Phillips who pioneered actually methods to cool and trap atoms with laser light, and they received the Nobel Prize in 1997. Again, a lot of quantum optics, the results in quantum optics were used because this is all about how to cool and trap atoms with laser light. So basically using the momentum or the particle nature of light. That was one important event. Then in 2001, Wolfgang Ketterle, Cornell, and Wieman, they achieved the Nobel Prize for Bose-Einstein condensation in dilute gases of alkali atoms. Now, these are mostly with atoms. So this is atom-light matter interaction, but that's also an important aspect and wouldn't have been possible without developments in quantum optics. Then in 2005, it was Theodor Hansch, Glauber, and Hall who received the Nobel Prize for their contribution to, actually it was Glauber for his contribution to quantum theory of optical coherence. And the other half of the Nobel Prize was actually jointly shared by John Hall and Theodor Hansch for their contribution to the development of laser-based precision spectroscopy, including the optical frequency comb technique. So again, an important one. Then in 2012, the Nobel Prize was given to Sergei Harosh and David Wineland for their for the groundbreaking experimental methods that they developed that enabled measuring and manipulating individual quantum systems. So again, so this was at the level of individual quanta, like single atom, single photon, kind of experiments. So, and managing all of that was possible, again, through the quantum nature of light. And ultimately, so very recently, last year, we are very proud in the community, again, for this Nobel Prize in Physics, which was given to Ale Aspe, John F. Clauser, and Anton Zeilinger, for their experiments with entangled photons, establishing the violation of Bell inequality and pioneering quantum information science. So proud to flash this slide, and it's a proud moment for the community, because this was an award that was long awaited, and yeah, and it was very it couldn't have been, so there's a lot of endeavor all across the world with entangled sources pertaining to quantum communication, and also for other things such as in quantum computation. So just to give you a glimpse, since continuing with this last Nobel Prize, so maybe I need not explain to this community what is entanglement. Students already know it. So entanglement is a phenomena that occurs when a group of particles are in a joint state, very the way we explain it. And that joint state, the group of particles are entangled because of some generation or interaction had happened in such a way that the quantum state of each particle cannot be described independently as we know it. And when we say it cannot be described independently, so mathematically we say that the quantum state, or the joint entangled state cannot be written as a product of the individual state of the particles, right? So it cannot be factored out. So that's the signature of an entangled state. And so these particles who are entangled, they share correlations in their quantum states, even though they seem to be non-interacting, and they can be spatially separated. So this was the bizarre, spooky action at a distance about which quantum. Einstein had a question. So those are the popular aspects. That's the way we popularize. Also, it's very popular in those aspects. Now the applications are actually several. I've just shown a few pictures here, but as we know, just the broad application. So it's pretty much utilized in the field of quantum computation, because entanglement allows to enhance the efficiency of certain algorithms with respect to their classical counterparts. So that has a lot of application there. Then needless to say, entanglement has huge application in quantum secure communication, both in free space satellite as well as fiber communication. There's quantum cryptography, quantum key distribution, and particularly the entanglement based descriptions, which are highly secure in comparison to the single photon based communication protocols. And another application of entanglement is also in quantum networks, where we actually work with, so I've just talked about photons and atoms, but instead of atoms you can also have any other stationary node. So information, if you want to transfer from one node to another node, typically you would need quantum channels, but with the help of entanglement, if two photons are entangled, and if you allow these two photons to go and interact with two nodes, then the two nodes are also entangled in a way. So this is like entanglement transfer and also entanglement distribution that is utilized in quantum networks. So yeah, maybe I could, this is the slide I was just explaining. So this everybody knows, I think. We cannot write the entangled state as a product of the individual state of the particles. Here I've taken a bipartite system. So let's say typically, you know, if you're talking about two photons, the signal and the idler. And some of these states are the famous Bell states, the two particle systems. And there's a misprint here. So there's the phi plus minus states, which are typically, you know, similar properties in the signal and idler in both ways. And the other two Bell states, which are psi plus minus, which are dissimilar properties of the signal and idler. So here 0 and 1 are actually the qubits in quantum system. But typically, I mean, in photons, these are different degrees of freedom. In atoms, there are different degrees of freedom. Now, particularly if you're talking about entangled photons, you can have systems which are built in free space. So photons come out in free space, and it's a free space experiment, and you can have entanglement of states like that. A very famous, you know, so also in the cover page of Scully Zuberi, which is a book on quantum optics, you have this famous ring picture, the two intersecting rings from a Bibo crystal, which shows that the photons are entangled in the region of their intersection. So, so that's possible in free space. But on the other hand, you also have fiber-based experiments, which are very lucrative, particularly, you know, in telecom quantum communication applications, where, and in both these scenarios, you can have entangled systems. Now, just going a little bit beyond the entangled systems, there is, you know, there are emerging technologies in quantum information and quantum computation, quantum communication, right? So as we know, these are quantum computers with single ion superconducting qubits. I thought I'll just flash this slide. And then there is also communication with single photons. So these are several systems. There are more actually. These are not very recent pictures, but there's a lot that's going on in quantum information and quantum communication as we know it, and quantum computation. There's a big development, and you know, several countries are funding a lot towards research in this direction, as we all know it. So maybe I could skip some of these slides because these are very basic. This is just, you know, qubits to compare with, you know, a classical bit and a qubit. As we all know, qubits can be in a superposition of the basis states. So if you have n qubits, you have 2 to the power of n basis states. But in terms of those basis states, you can write out any other arbitrary quantum state as a superposition state. So, I mean, in that sense, actually, quantum information science utilizing qubits have a powerful perspective because it allows to exponentially expand the state space available for computation in comparison to classical computation as we know it. So what are the examples of a physical qubit? So a qubit could be anything. You just need a quantum physical system. So these physical systems, you can realize it through photons, or you can have atoms, electrons, spins, you know, quantum dots, etc. Superconducting qubits, all of that. Now, typically, when we're talking about photons, there are several degrees of freedoms. We talk about polarization, we talk about orbital angular momentum. So these polarization is actually bidimensional. Orbital angular momentum is actually, the dimensionality is very high. There's no limit actually, but for practical experiments, of course, you have, and these things are very interesting. So that's another degree of freedom. Typically, there could be also other degrees of freedom, like the presence or absence of a photon in a particular path, and all of that. So utilizing all these degrees of freedom, you can have different kinds of entangled states. Now, qubits, you normally classify qubits. Okay, I forgot to mention. So that in atoms, you are usually talking about two-level systems, two-level energies that you try to see. And so these are typically the 0 and the 1 states. And any atom could be in a superposition, a coherent superposition of these two levels. Then in electron spins, you also have the up spin and down spin. So you can write out different qubits. So these are physical systems that can act like a qubit, and there are so you can write out qubit states, or you have to properly prepare these systems in order to realize qubit operations and all of that. So qubits, if you have to classify them broadly, these are stationary qubits which are localized in space. So these are typically, systems that can act as a quantum memory and a processor. And these are localized or stationary. So these could be internal states of neutral atoms, internal states of ions, nuclear spins of molecules. Then in solid state systems, it could be superconducting circuits, quantum dots, etc. Right? Now, the other broad classification are flying qubits, qubits that are mobile, so they can travel across space. They are not localized, and so we call it typically the moving carriers of quantum information, and typically these can serve as quantum channels in a quantum network. So as I mentioned already, it could be through photons, so polarization state of a photon. It could be the presence or absence of a photon. It could be also spin state of electrons, etc. So mobile qubits and stationary qubits. So that's the broad classification. So utilizing all of this, is the field of quantum information. And this is a slide maybe I'll just skip in this QIQT thing, just to tell you that so there is a comparison, but you have a lot in quantum information, which is not there in classical information processing, particularly the solid points where quantum information is in an upper hand is the superposition principle, in aspect of which you can have a large number of states and large number of, the computational space really gets expanded. Then there is the powerful resource of entanglement, utilizing which you can have lots of other possibilities. So with that, I think I'll come to the techniques of producing single and entangled photons. As we know it, one particular technique which is really the workhorse technique is spontaneous parametric down conversion, as I briefly mentioned it once earlier. So this is the nonlinear optical technique utilizing the second order nonlinearity inside a crystal. Some of the examples of popular crystals are BBO, beta borate, then lithium niobate, potassium tantalum phosphate, KTP, basically, and then there are several others, but these are some of the popular examples. So this technique takes place under the conservation of energy and momentum. So there is a single pump photon whose frequency should match with the emitted, some of the frequencies of the emitted signal and idler photon. So that's the conservation of energy, which is always maintained. Typically, you start with so if you're doing a free space experiment, typically we start with, if you start with 400 nanometers and produce degenerate signal idler photons, you'll be emitting 800 nanometer signal and 800 nanometer idler. But these are also, although they are emitted, so there is a central line, but these photons are in a broadband emission. So there is a bandwidth of emission, and across that bandwidth, the signal and idler are emitted, conserving energy, keeping that in feature. So apart from energy conservation, there's also momentum conservation. As we know it, the momentum of the signal and the idler photons should actually match up to the momentum of the pump photon. But due to dispersion, inherent dispersion in the medium, this is not particularly fulfilled, and there is a small momentum phase mismatch, which we also call as the phase mismatch. And typically there are techniques in nonlinear optics such as birefringence phase matching and quasi-phase matching that takes care of this mismatch. And then you can have crystals where you have a high efficiency of generation of signal and idler, and near perfect conservation of momentum there. Now these photons, there could be different kinds of phase matching, but they can be typically entangled into states which are like this. Now, SPDC, so there could be different kinds. So there could be non-collinear, and the photons could be non-degenerate. Then sometimes they could be non-collinear, but the photons are degenerate, where the two cones actually are superposed because they are degenerate. Then there could be also collinear phase matching, where the photons are coming out in approximately, in a, so we use the paraxial approximation, and it's like, they're coming out in one particular direction. So that's collinear phase matching. and all those things are possible. Then there are different kinds of polarization, properties of the signal and idler that are generated. So, and we classify it into type 0, type 1, and type 2, as people know it in the community. So type 0 is a process where all three photons, the pump, signal, and idler, they have the same polarization. Type 1 is where the signal and idler have the same polarization, but it's orthogonal to the pump photon that you've shined in. And then type 2 is the signal and the idler, which are the emitted photons. They are orthogonal in polarization to each other. So those are different kinds of classifications. Now that is about SPDC, another very popular technique. Now it's becoming also very hot, and there are lots of systems that are coming out in this, is spontaneous four-wave mixing. So just like spontaneous parametric down conversion, which is a nonlinear QIQT process, this is a nonlinear QIQT3 process, utilizing the third order nonlinear optical nonlinearity in an nonlinear optical crystal. And the popular example of such systems are actually silicon nitride. Silicon based systems have high QIQT3. So here typically there are two pump photons, because this is four-wave mixing. So all these four photons actually get mixed together. That's why the term four-wave mixing. And the things happen in the spontaneous regime where we are like utilizing very low powers of the pump photons. So there are two pump photons instead of the one that we talked about. So this is just a comparison with the SPDC. Here I have a similar picture. So the two pump photons mix in such a way. So here I've drawn degenerate photons, but you can also have non-degenerate pump photons. But experimentally, it's a little difficult to work with non-degenerate pump photons. So you have degenerate pump photons, and that can break up into signal and idler photons, which are of different frequency, and they could also be degenerate. So this is so if, let's say, if omega p1 and p2, they are equal, then you have twice of omega p, and this is the energy conservation. That should be equal to omega s plus omega I, which are the frequencies of the signal and idler. So here momentum conservation is again, satisfying, just like we have it there. We write in terms of beta, because these are typically, these things are utilized in nano waveguides or micro ring resonators of silicon. So these are inside a guided system. We usually talk about beta and not K, which is in free space system. And so this is the momentum of the pump photon. So there are, this is twice beta P is equal to beta S plus beta I. And the phase mismatch term is actually, comprising, so we do a Taylor expansion of all of this. And there are these terms, which are the second order derivative, which is the group velocity dispersion term. And then there is the fourth order dispersion term for this. And utilizing these two, actually phase matching curves are drawn. So the shape of this phase mismatch curve actually depends on the waveguide dimensions, because these dimensions are very small. They are like typically nanometers, so several hundreds of nanometers, but still they are much smaller than the dimensions that we use for SPDC, for example. So these waveguide dimensions actually, and as well as the pump wavelength, all of this actually dominate your phase mismatch curve. And typically through dispersion engineering, by playing with the dimensions of this waveguide as well as the pump wavelength, you can actually phase match certain processes and particular things that you require. So this has also become very handy. So you can have, based on these sources, silicon, nano waveguide sources or silicon on insulator sources, you can have heralded single photon sources, or you can also have, which are spectrally pure sources, typically decorrelated photons, as well as you can also have polarization entangled sources. Right, so this is also a field that is very popular, and that technique is quite this thing. So now coming to the results from our group. So this is just a nutshell. Maybe I will not, I'm just looking at the clock, so there's not much time, but I'll just briefly talk about some of the results and the aspects in which we are working on. So our group is the Quantum Photonics group based in the Department of Physics in IIT Delhi. And we work on several regimes. We work on quantum communication, so we have experiments on fiber-based quantum communication as well as free space quantum communication. We are also interested in quantum sensing through quantum detection through squeeze light, basically, which is a waveguide based experiment that we are just starting and we are exploring. We have several sources actually on all these aspects. As I mentioned, we also work on correlated photons in nano waveguides of silicon. This is one regime utilizing 4-wave mixing. All these other blocks, actually, we utilize SPDC. And we also, something little different from all of this is another interest of the group, which is coherent light matter interaction in atomic media. Here, actually, we wish to look at, effects such as coherent population trapping and electromagnetically induced transparency, which are also very hot and, very, very important effects where you're talking about, so in aspects of optical storage, quantum memory, and all of that, if you want it in an atomic system. So currently, we are just starting our experiments. We have a vapor cell at room temperature. So we don't do any cold atoms. We work at room temperature and hot atomic systems, but there's a lot that you can do even with those systems. So that's also one of the interests. But today we'll not have the time, of course, to talk about that. So I'll just try to touch upon a few of this. So before we go on, and this is an important slide. This is our group, and I mean, all the work, all the results are from this group. Students work very hard, and we also continuously and fully, actually, we share the group with Professor Vivek Venkatraman in electrical engineering in IIT Delhi. So this is a mention, and this is our current group. So we have several PhD students as well as postdoc. There's so some of the mentions are Shivani Sharma and Vijay, who are working on the silicon nano waveguide system. Then we have Om Shankar, who's working on the free space system, free space quantum communication system utilizing SPDC. We have Rajni Bala and Bharti, who are working on the coherent light matter interaction in rubidium vapor at room temperature and hotter, temperatures. Then there is Vikash Yadav and Akansha Angural, who are working in the fiber-based system for quantum communication, and Akansha particularly is also working on the generation of squeeze light. So, and there's Dr. Mitali Sisodia, who's currently our postdoc, who's also associated with the Free Space Quantum Communication Project. So there are past members from the group. So yeah. Now, these are some pictures from the lab. There are more, actually. This is just to show you that this is one side from the lab. This is another side from the lab. And this is the free space quantum communication experiment, the initial, experiment when we were setting it up. This is a glimpse again of, these are older pictures, again, of the fiber-based system that we have. Now, things look a little different on the table. So as I mentioned, so we work on both the optical band, utilizing free space quantum communication, which is, so we typically work at 800 nanometer photons for the generation of 800 nanometer photons. And we also work on the telecom band for the generation of photons around 1550 nanometer, but, spanning which, we have systems which are very broadband. So utilizing SPDC, actually, we have systems which are like 50 nanometers broad, starting from 1520 to 1580 nanometers. In silicon, actually, we span the entire telecom band, and in fact more than that. It's a much broader bandwidth utilizing silicon. So all these could be used for fiber-based quantum communication towards multi-user kind of quantum communication. And on the other hand, the free space system could be utilized for free space optical or satellite communication. So these are sources that we are developing, and we have applications in all of that. So all these systems are actually entangled, and as we know, so if you consider entangled systems in contradiction to the so there are different kinds of QKT protocols. We can broadly classify them as prepare and measure based protocols, which are single photon based, such as BB84 and B92. Here, in case if you're using attenuated laser pulses, then they are prone to PNS attack and intercept recent attack. But if you're using true single photon sources, then those attacks are they are safeguarded. But on the other hand, there are also entanglement-based protocols in QKD, which are dependent on entangled photons particularly, and these are the QIQT23 protocol as well as BBM92 protocols, and these are much secured compared to the other ones. So again, there is inherent randomness of these sources, which actually contributes towards the security aspect of these protocols. Then they are resilient to eavesdropping attack. There is also longer transmission paths which are possible. Then there is inherent source independent security and all of that. So entanglement-based protocols are very lucrative and powerful in those aspects. I'll just skip. So there are different ways in which you can utilize them. And so one of our first experiments, which is the free space experiment, here actually the main application of this experiment is to link establish free space optical links that are required for distance communication among areas which are not suitable for fiber installation or for moving terminals, right? So here we wish to actually generate photon pairs which have hybrid properties based on both polarization as well as orbital angular momentum. And just excuse me. And so maybe I will not have the time to get into a lot of details in this, but I would just like to quickly show that in this regard, we actually have results. So we actually shine in a laser at 400 nanometers, and we have a PPKTP crystal, and we have recently seen entanglement-based results on this, and this is our quantum state tomography that we have. So polarization entanglement is established, but we need to improve our results because our fidelity is not very high. Nevertheless, and so this is currently polarization entangled, but we would like to go on to the next steps of hybrid entanglement, utilizing both polarization as well as orbital angular momentum. And therefore, this could be applied towards an entanglement-based QKD. The other experiment, which is the fiber-based experiment that we have, this is a broadband telecom photon source. It's a very bright source. So this is a ohmic number. Currently, we have improved our source, and the number is, the generated brightness is about 10 to the power of 8 pairs per second per milliwatt per nanometer. And this is a broadband source again with a very high CAR value, as well as I mentioned, high spectral brightness. And recently, utilizing a SINAC interferometer that we have, this is an all fiber, all WDM, all waveguide based source. We have achieved again polarization entanglement in a different entangled state, which is HH plus VV. And since this is very broadband, centered at 1550 nanometer, the broadband fidelity of entanglement is actually very high. It's around 92.2%. And also the channelized fidelity is very high. So there is also channel to channel entanglement. So this is currently our result. So that's one of the direction. We also work on several, designs of several integrated architectures to produce, post-selection free hyperentangled photons, swappable hyperentangled photons, everything that's waveguide based. And the architectures are typically in lithium niobate and PPKTP. So these are designs that that could be very hot if companies can take up the fabrication aspect of it. So yeah, that's one thing. And now a little bit of update on the silicon on insulator nano waveguides. So as I mentioned, so these utilizing SOI platforms, you can also have integrated quantum light sources at telecom wavelengths, and these are typically very broadband based, and they have applications again on single photon for the development of single photon sources, or entangled photon pair sources, which have their own applications. And the one important difference with SPDC is that the photons are generated in the same band as the pump, and in these processes there is low time jitter, and the phase matching of these systems are through dispersion engineering, as I mentioned before. And there is broadband, ultra broadband, that is possible for phase matching. So typically from 1.4 to 1.7 micrometers, you can phase match these processes, and therefore this could be utilized again towards a multi-user quantum communication protocol. So I'll just skip this slide. Silicon is hot because it has a very high refractive index contrast. It has a very high Kerr non-linearity, and that's why it's hot. So high Chi3 basically. And this is a slide, maybe I could just skip. This is just to show you that there are some designs that we did, and we also have a chip comprising of several nano waveguides of silicon on a chip. And these are the nano waveguides. This is a picture that we have, and this is the typically one of the waveguides. So these have to be grating coupled because these are very small in dimension. So it's not very easy to just have them coupled through a fiber or in free space, right? So you need grating couplers for this, which are actually etched in the same. It's part of the design. And based on our designs, actually some of these waveguides were fabricated in IIT Madras in the group of Professor Vijay Krishna Das, and these were experimented for the classical 4-wave mixing signal, and these are the experimental results based on the designs. And so this is the central pump, which is at 1550 nanometer, because we use a pump source at 1550. And in the classical 4-wave mixing signal, you need a stimulating signal laser as well, which is utilized, and with the help of EDFA, of fiber amplifier, this experiment is done. And as you can typically see, these are this is the way we couple light into these systems. So there has to be a system, a free space system, and to couple light through the grating couplers and into the waveguides. We tested all these waveguides, and these are some of the results. So there is signal and idler that are emitted, and we could see these 4-wave mixing signals based on our designs. So now these designs, if you don't, so these were in typical 220 nanometers of thickness, which is the most popular because silicon wafers are available in 220 nanometers thickness. But if we could go to slightly different thickness, because one disadvantage of using one disadvantage of silicon nano waveguides, just typically the TM polarization is actually not that well phase matched. The T polarization is phase matched, which means that there's the photons that are emitted, which is signal and idler, basically, these are always similarly polarized, right? So now if we want to have entangled states, we would also like to have both polarizations that can be generated out of such systems, right? So H and V, or typically T or TM polarization through these SOI waveguides, nano waveguides, right? So then we actually there are ways, there are experiments that have been done, but they are like there's something done outside the system. But we thought we would try to play with the dimensions and see if the dimensions could be changed, and if it could be this process of both polarizations being phase matched through dispersion engineering, if this could be possible by playing with the dimensions. And then we came up with a thickness of 280 nanometers of the silicon nano waveguides, and of course I'm telling you in a nutshell. So there are other things that has to be tackled at the same time. And here we see that when the thickness is varied, and of course, the widths and everything are varied, we came up with designs where both the polarizations, T as well as TM, are equally, you know, there is a probability of generating T and TM equally with equal probability from such sources. So based on that, actually, we have our this one that got highlighted, and this is a new work, and I'm happy to share that. And I think I would stop here. There will not be time to talk about this last thing, which I want to talk about networks, because it's already 11. Should I stop here, or is there a couple of minutes?
Yeah, you can stop here so that people can, if
Yes,
some
yes.
questions are there, they can ask. Yeah,
Sure. Yeah.
it will be better. So if there are any questions, you can unmute and ask questions directly to speaker. We have enough participants. Any of the participants, please unmute and ask questions you have, if you have.
I have one question.
Yes.
Thank you. Very interesting talk. In free space, what type of loss mechanisms like diffraction you consider when light propagates in the free space?
Very good. So thanks for that question. Actually, I did not have time to detail. I should go to that slide. I actually had to skip. So there are slides in between. So it's not, you know, it's not a one-day experiment. This is an experiment that we do in free space. Okay, the other experiments are mostly waveguide based. So here, if you see, so this is a crystal of dimension of a few micrometers, let's say. And you need to no, this is a crystal in free space, so it's in dimension of a few millimeters, but still you know, we have light which is free space out of a laser. So this is the collimated beam is about 2 millimeters or 3 millimeters in dimension, and then typically we use lenses and then focus them into the crystal. Now, due to this, so then, you know, beyond this, you know, we see that Gaussian beam propagation actually affects our results. And I don't have currently a slide, but we, if you go to this particular paper, which got published in Journal of Optics this year, here we have in detail, you know, explored the impact of focusing on the second harmonic generation signal that we see from this crystal. So this is this current setup is for SPDC, and the same actually we also see it in SPDC. But when we characterize our crystal, we first, of course, do play with SHG, which is the reverse process of SPDC, and there we saw that the SHG signal, you know, became asymmetric to symmetric when we change the focusing lenses. And this has, you know, there is a play between interplay between the wave, the spot size, you know, because we want the spot size to be as small as possible, because the nonlinear interaction should be, you know, enhanced when you go to a smaller spot size. But the same, when you go to smaller and smaller spot size, the diffraction effects inside the crystal also enhances, and this leads to asymmetric. So the SHG, if you plot a graph of the SHG from this crystal, the second harmonically generated power from this crystal as a function of the temperature, so that's typically a sink curve, but that is good, and that's supposed to be symmetric as a function of the temperature, but that becomes asymmetric when you focus it too much. Right? So as a function of that focusing parameter, we came into a regime where we can say that we are more or less in the Rayleigh regime, and you know, it has a strong impact also on the amount of SHG power that we can actually get out of the crystal. So that's a detailed study. So if you really need details of that, please go for more details in our paper. Yeah. And actually, there are also interesting experiments, because we also played with light with OM property, and SHG is automatically affected. So this impact of focusing is actually seen in both lights. When we start with a pump with homogeneous polarization, and then a pump which has inhomogeneous polarization, typically a radially polarized or azimuthally polarized beam, which has OM content, basically. So there are interesting results in this paper. Please.
So, Joy, we have one question in the chat. How
Chat box.
photons are entangled based on orbital angular momentum?
Okay, so
From Vishnu. Yeah.
from Vishnu, yes. So orbital angular momentum. So maybe I could go to that slide.
Mm.
So okay, so typically, actually, there are other ways just based on orbital angular momentum. You can have systems, particularly these signal and idler system, where one can have different OM content in this. So if you start with a pump that has zero, let's say OM, then or maybe let's say 1 L equal to 1, then you can have signal and idler. So either, since OM has to be conserved, so either the signal will have OM L equal to 0 and the pump will and the idler will have OM equal to 1, or the reverse, right? And then one can typically uh, uh, have them into entangled state. But what we do in this particular project is actually we utilize both polarization as well as here we use a pump which has 0 OM content. So SPDC, we are using a pump that has 0 OM content, but we have systems, OM manipulators like Q plates, which can actually so if you start on with some circular polarized light, this is a picture of a Q plate where the OM, so you start with a circular polarized light and OM content 0, right? So with the help of a Q plate of topological charge Q is equal to half, you can convert it to a right circularly polarized beam and with OM content +1. Okay, and similarly, if you start with an RCP beam with OM 0, the same Q plate actually can convert it to LCP and OM -1. So typically, if you have OM as well as polarization, so these are actually hybrid qubits where we want to have them entangled in hybrid property. So both polarization as well as entanglement, in OM. I don't know if I could explain it very well, but yeah, I don't have slides actually to explain just on, because so with the help of what do I say? Yeah, I don't have a slide here to
It's okay.
explain.
It's okay, Joy. Yeah, it's okay. You have explained pretty well. Yeah, don't worry.
Okay.
You have got thank you also from Vishnu. Don't worry.
Yeah, I see that.
So, any other question? Just one more question we will have.
Yeah.
We are getting late. It's already 11:10.
Yeah, there's the next talk by
Yeah,
Gautam.
Gautami.
Yes,
Yeah.
yeah.
So,
any
any other question?
Can I ask one more question? So,
yeah,
okay, last question then. Yeah.
Okay. So on slide number 23.
Oh, okay, let me go on.
What
was the question? Can you?
Yes, the state on the left below corner should be symmetric because photons possess boson statistics. The question is, but here minus sign is present. Is it misprint?
Where is it? Where are you looking at? This one.
He's saying HP minus VH you are getting. Why you are getting minus sign? He's saying according to him it should be minus. If there is misprint, that's right. That's what he's asking.
In this one? In the first one?
In this one, yeah. In this one, yeah.
Free space one? No, so this is, it could be both plus and minus, but so from the quantum state tomography, I mean, there has been, evidence of this fact. Typically, these ring structure actually entangles the photons in this singlet state. So it is with this minus. So so these experiments, whether, so in free space system, you can have it also plus, but these are typically, I don't know. So I don't know, RP. I mean, how should we?
You can have all the four Bell states.
Have all the
four states you can make, yeah. Plus, minus both. HH plus VV, HH minus VV, HV plus VH, and
exactly.
all four are possible. You can make it. It's not a problem, yeah.
Yeah,
But
but these,
Joyee, I
yeah.
would think that this should imply the space part will be correlated such that the overall two photon wave function will be symmetric, no?
Yeah, overall two photon wave function is selected in the experiment. Of course, we use small laser power beams, right? And we are only looking at these two portions where there is an where there is an intersection, right? So we actually scan our detectors and we only look at these. So the selection is very specific. We don't look at the entire ring. So only these two selections, and of course, with the assumption that we're only looking at two photon system. This is the thing. But otherwise, I mean, as we know it in SPDC, of course, there you can put it as a summation of different multi-photon systems. But typically, we are in that low regime where we are operating at high car values. So there's a there's this. So when we do our characterization, we keep very low powers and we see this coincidences to accidental ratio, which is typically very high, which shows a very high G2, and that happens for very small pump powers, where we can safely say that you're mostly producing two photon, biphoton states, and the multi-photon states are really very low in probability. So under that assumption, we have actually put the signal and the idler. But actually, I mean, in a real picture, actually, there are many terms. But this is, I mean, like you can assume it for low pump powers, you can assume it to be by photon systems. And typically, if you just look into these two portions, so there is a detector here. So counts from here are counted, and then there is a detector 2 that are counted. And only when you do a correlation experiment, so you plug in the two detectors in a coincidence counter, you should get this particular state. And it's always like if this is the horizontal cone and this is the vertical cone, let's say, then these two portions, these two intersection regions are the ambiguous regions. And only when we do a correlation, a coincidence of these two, it actually projects it onto the singlet state, which is minus.
Thank
In
you.
this free space experiment, this is always a minus. Yeah.
Okay. Thank you, Joyee. Let's thank Joyee once again for a very nice talk. Gautam, you can also clap for Joyee.
Sorry, Gautam, that took a very long.
No problem, no problem. It was a nice talk. I was enjoying it.
Okay, so Joyee, you can leave and we can introduce Gautam.